During the late 1970s, there was a boxcar shortage that caused problems on American railroads. This had adverse effects on industries like agriculture because transport needs couldn't accommodate production demands, and stores of perishables like wheat went bad in warehouses because they were unable to be transported. A boxcar, if you're unfamiliar, is a type of a railroad freight car popular in the early 70s, and it was designed for transporting cargo over long distances. Money was tight in the railroad industry in the 70s, and railroad companies were struggling to afford modernized cars to handle specialized loads like wheat and grain. Neither could they afford modernized cars, and so there were few cars on tracks, and even fewer to haul these loads. There was also the problem of resource distribution. Because there were fewer boxcars, and boxcars at the time were associated with railroad companies, the cars had to be sent back and forth between customers and railroad companies, and every car on the track at the time was largely underutilized. This led to the introduction of the incentive per diem car, or the IPD boxcar, which encouraged short lines or smaller railroads to invest and rent that car to larger Class 1 railroads, which were handling these giant customers on a per diem basis. So if you had a small railroad like the Port Huron and Detroit Railroad, they would rent a car to a giant Class 1 railroad like the Grand Trunk Western, I think is what it's called. And so cars on tracks were always utilized, and there was a return on investment for the smaller railroad companies because there was priority loading for those newer railroad cars. The boxcar shortage and the introduction of these rail cars, these incentive per diem cars, highlights the importance of composability and agility when it comes to handling scale, and how leaning on an existing infrastructure can reap benefits when it comes to scaling effectively and efficiently. I bet you didn't think I was going to give you fun train facts, but here we are. Now let's imagine that these cars are instances of our applications. In order for us to send an application from east to west, or across the globe for that matter, we could, like the railroads were doing before the shortage, manage and create our own rail cars. But of course, this is incredibly inefficient. Or we could take advantage of an existing infrastructure, an edge infrastructure, and deploy applications closer to our users, similar to what the incentive per diem boxcars encouraged. So instead of us heavily investing in infrastructure and provisioning servers ourselves, we can lean on an existing edge infrastructure to provide that global accessibility for our applications. Of course, I'm assuming here that a lot of deployments are easy, and they are not. It's not just a matter of renting infrastructure. We also have to understand how applications can be built and managed. Yes. To deploy an app globally, we have a lot of options, and we have a lot of workflows, and we have a lot of systems, because distributed systems is very, very difficult. But for the purposes of this talk, I want to specifically talk about the journey of an app deployment and focus on the packaging and distribution of an app, and how this process has changed and evolved with time and technology. This is the story of the little app that could. Now let's imagine that we have a full-fledged full-stack app. Like we have a front end, we have a back end, we have whatever other services associated with it. And let's say that we want this application to run in multiple regions, in multiple ways. We want to be able to quickly spin instances of it up and down. And we want to ensure that things work consistently, regardless of host and location. To do this, we define a set of instructions on how an app can be run. So this includes application dependencies, libraries, an operating system, or runtime, whatever your app will need to run. So we want to make sure that an application run for one system will not accidentally run in another, because obviously it will not work. And in deployment terminology, this set of instructions is called an image. And it is with this that we create instances of our app. Images form the foundation of how we deploy. It's the blueprint or the template by which we tell an app how to build and run, or we tell the environment in which the app runs to run. And in a way, an image is a glorified tarball, if you think about it, because we are just using that as a set of instructions to build, which is what a tarball was. And it is with this lens, or this as a compass, that we map app deployments, or at least I will, in the time of this talk. And so app deployments happen in two main ways. You have virtualization and you have containerization. In virtualization, you start with a virtual machine image, which contains an app, it has dependencies, it has libraries, and most importantly, it has an operating system. And here, the image uses that operating system to know how to run that application. It's really important, and it creates that isolated environment so that you can have multiple applications running on a single piece of hardware. In containers, we create a container image, so it's very similar in terminology, but actually really different in terms of what you're doing. Because here, a container image is a standalone executable, and it includes an app dependencies and all of these, but it does not include an operating system. Instead, it includes a runtime, and this is essentially what your application or what the container environment will use to run your apps. The contrary piece to this, or the difference with virtual machines, is that you no longer have an operating system, you have a shared operating system. So every container has access to that shared operating system and operates that way. There's benefits and drawbacks to either. I don't want to put shade on one or another because there are benefits, again, to either. But I want to talk about how we have gone as an industry from virtualization towards containerization. I always forget about my animations when it happens. Virtualization via virtual machines is a popular method. Well, it was, and it kind of still is, at least for legacy applications. It's a popular method for deploying apps if you want that complete isolation in a multi-tenant environment. The main goal here is to distribute underlying physical resources. So these are resources like CPU, memory, storage, networking, and this is what every single application will have access to. Prior to virtualization, this is just an image of how architectures used to work. Traditionally, you would have a one-to-one mapping between your app and your server. So if you wanted a new application, you would basically have to provision a new server. And you can tell as you scale, this becomes really untenable. VMs offer this many-to-one approach. So you're able to pack in multiple apps within that single space. The way it does this is through a virtualization layer, which is what you see between the physical hardware and the apps. And this virtualization layer is what virtualizes the physical underlying hardware. This virtualization layer is also called the hypervisor. Historically, this was a type 1 or bare metal. I won't be talking about type 2 or hosted because there's not many use cases for them. They exist, but they're not as common. And this hypervisor is essentially running on the metal. And this hypervisor has direct access to physical resources. So the guest operating system that's above, when I say guest OS, I just mean whatever the VM contains. It doesn't actually have any idea that it has been virtualized. It sort of assumes that it's actual hardware and it runs as if it's native. So from a user perspective, you have that native you have like a performance boost in terms of running on bare metal. There's obviously trade-offs, which I'll talk about in a second. But that is generally the benefit to using VMs. So when you build on a hypervisor, you create a VM image. And this is basically what creates those instances of our app. And every VM image is tailor-made to the hypervisor it's built on. So we might have a Zen hypervisor, which has certain drivers and modules. You might have a KVM or kernel-based virtual machine, which again, in KVM world, I'll talk about it again a bit later, but in KVM world, you need Camus and other drivers in order for it to work. And so when you create that virtual machine image, you really have to take into account all of these pieces. And you might even need extra XML files or configurations in order for things to work, because machines are really dumb, and they need to know how things work. So you need to configure them within the VM image. So that's basically what a VM image is. And if you were to apply this in practice, like this is just a quick run through of EC2, which many of you probably have used, but you would basically create a VM via their UI. There's other ways to do it, obviously, but this is a contrived example. But you would pick or you would augment an AMI or Amazon machine image. And this is basically what tells EC2 how to run or how to build your environment. And Amazon or EC2 is specifically built on Zen. So from the previous slide when I showed you those hypervisor pieces, it has certain configurations that are really, really specific to that. And in most cases, if you stick to that hypervisor, if you stick to a specific hypervisor across your hosts, you're fine, because VM images can sort of be translated similarly but differently a little bit. But the moment you move away from a vendor or provider or a hypervisor, like if you went from EC2 and you're like, I'm going to use ESXi now, well, you have a different image that you have to create, because a lot of hypervisors have proprietary technology associated with their VM types. I hate how this image replays. It's fine. And so the thing with multiple hosts and multiple hypervisors, or wanting to support multiple types of hypervisors, is that you now have the problem of having multiple images. So already as is, handling a VM image can be convoluted, but if you are wanting to support multiple hypervisors, you have that added layer of complexity. What's more, if you wanted to create a distributed high availability system, it becomes more complex, because in traditional environments, we configure VMs sort of manually. Does this like, oh no, I have to click each time. And so the nice thing with modern hypervisors is that they offer automation and orchestration. And so you can do a lot of things within that system. But of course, there's limitations within that, which is a little frustrating. I don't know how many of you have worked with hypervisors or VMs, but there's a bit of like a learning curve that is associated with it. And then if you want to create like a failover cluster or redundancy, you have added complexity that takes a lot of time, and it can be really error prone, because again, creating a robust system requires understanding it, which requires tooling to understand, and it sort of moves further and further. And so all in all, you can imagine that managing VM instances becomes unwieldy as your app scales. I don't know how many of these I put on this slide, so I'm just gonna click till, okay. So from the woes or from the problems of virtualization, again, like I don't mean any shade in terms of virtualization, but a lot of the problems that we have faced has led to the introduction or the movement towards containers. And containers was popularized in 2013 by Docker, but it was not exclusively a Docker project, because containers actually goes much further back. I don't know the specific time, but if you know in Linux containers, and chroot was created in BSD jails, around that time was when the concept of containers came about. And containers actually stands on the principles of like Linux kernel features, namely C groups and namespaces, which I'll cover in just a second. But the idea here is that containers moves virtualization up the stack. So instead of virtualizing the hardware, we're virtualizing the operating system. This means that, as I said, a single host OS is shared amongst containers. So we have that shared piece of operating system, but each container still has an isolated file system. So there is a level of isolation, even though it's not the complete isolation that you saw with VMs. And in this method, specifically why it's really handy and really popular is because you no longer have to think about operating system intricacies. So you don't have to plan resources ahead of time. You don't have to think about how your app will really run. You just have to think about how your app logic works and maybe the specific runtime in which you want it to work. When deploying these, it actually leads to more lightweight images. So with a VM, you're hosting you're building it with an entire operating system, which leads to like gigantic images. And in containers, you're not doing that anymore. So you have more lightweight, smaller containers or images. And this causes faster startup times, because smaller images means it's faster to spin up, which means faster startup times. And so I want to just dive into why this is the case and how this is the case, so we can better understand like why containers and why we should use them. So if you build a containerized application, which again, I assume most of you have, you would start with a Docker file. And in a Docker file, you typically create the image with this. So when you run Docker build, it will build that image for you. But you start with the Docker file, which is the set of instructions. So it denotes how you want your runtime to be, how you want your app to build, and how you want it to run, and various other things. And so you would define from the top a base image. So here I'm defining Alpine. You can use Ubuntu, whatever. But this is like the specific environment in which your app will run. You then add like app dependencies and your code and whatever else that you would need. And then you would also add like certain Docker directives. I think I highlighted them, yeah. So these are specific commands that you want your container to know about. So once it starts, it's like, okay, cool, I'm gonna do these things to make sure the application runs. So if you've used or if you've written anything that has like command or expose, those are Docker directives that are instructions for a image to run. And so once you have these, you basically build a Docker image. And as I mentioned, you'd use the API, so you use Docker build, and that builds the image. Most importantly, just to highlight the small images, the reason that happens is because Docker builds things in a layered file system. So when things are layered, it means that every command is a single layer. And so whenever you create a new change, or when you redeploy, it only deploys whatever the changed part of your app is, and it just reuses everything else. Because in the Docker internals, which I will not go into too much, there is a sense of caching. So Docker will cache a lot of the layers, and it will just reuse them if it doesn't realize or recognize that those have been changed. So this is what makes startup times really fast, and it's really, really nice if you worked with it. So the role the runtime plays, as I mentioned, is with regards to resource allocation. So you have the Linux kernel features, specifically namespaces and C groups, and this is what containers use to operate at in order to run things. And so namespaces isolate the processes, so they are the ones that sort of containerize your app. And control groups allocate the resources that your app will need. Most of the time, most of us will not be dealing with the runtime really, or adding any configurations here, but it's really important or really good to know, because if you are dealing with an orchestration engine, which I'm actually going to talk about in just a second, you would actually be dealing directly with the runtime. All of this is very straightforward. Docker makes our deployments a lot more, or the way we build and the way we deploy, really clean and seamless. But the moment you make changes to your, like not just your environment, environments is one thing because you can just create different Docker files and configurations. But the moment you have added complexity, Docker's simplicity becomes a double-edged sword. So for instance, if you have different types of hosts or different certain configurations that you want different apps to run in different regions, for example, you need to keep track of image versions. You need to keep track of network complexities in terms of how those containers talk to one another. And so there's, again, it's not perfect is really what I want to come to, that it is a movement forward in terms of how we build and deploy. But there is some added complexity. And of course, like you could use a container orchestrator, as I mentioned. And a container orchestrator is just like basically building on top of the container engine. So generally, a container engine is on the host. And if you're running a single container, you would just be operating at that layer. But when you have an orchestrator, it sort of communicates with that engine in order to run applications. So if you were to run Kubernetes, for example, you would have to install a container runtime on each node in your cluster, and then the orchestrator will be able to communicate and like send commands to every single node in your cluster. Conceptually, all of this is really straightforward, I think. But of course, the entire container ecosystem is sort of a nightmare. And again, no shade, but a lot of the composability and flexibility of this ecosystem comes from the Open Container Initiative, which has done amazing work in terms of open sourcing and making available all of these runtimes like runC and containerd, so we can plug and play things. The reverse side of it is that it means you have more things to understand because there's a lot of pieces that can plug and play. And so if you have any misconfigurations in your Docker or your entire like container orchestration engine, it sort of becomes really, really complex and frustrating to work with. And so without a doubt, virtualization and containerization have both been really, really important techniques that we have used as an industry to move forward with how we deploy and manage. However, as I said, it is not without its flaws. A VM, for example, might have the ability to create isolation, like complete isolation, but it comes at the cost of resource utilization. And of course, that means slower startup times. And containers, they're more lightweight. They give you kind of native kind of performance, but you obviously lose the isolation that VMs bring. You have some composability, but you sort of lose that aspect. But of course, it doesn't mean that they're both terrible or that you have to pick one between two terrible things, because the ecosystem has sort of moved towards creating more techniques. So for example, we have paravirtualization, or this is what micro VM and friends is, if you're familiar with that. And paravirtualization is also known as lightweight virtualization. So it sort of takes the concepts of virtualization and containers and puts them together. So you get the isolation of a VM and the composability of a container. So you get the best of both worlds, but not really. It's just specific for certain instances. I just want to mention that because micro VMs are fast, but they're very specialized for certain workloads. So in order to fully understand how this is faster, even though it's a VM, I just want to like go back to our virtualization concept. You have this virtualization hypervisor, or a virtual machine monitor, which is the hypervisor layer. And the hypervisor works as a virtualizing of physical hardware. So CPU, memory, all of that. It's great because we need that for our applications. But what comes with that is an entire computer, essentially. So you have peripheral devices. You have input devices like your mouse and your keyboard. You have output devices like your microphone. And so all of this is not really important or necessary for your computer to function or your app to function. But a VM comes with it anyway, because you're not telling it otherwise. And so what a micro VM does is it scales all of these down. It sort of understands that when you're running an application, you're likely never going to need a printer driver because servers don't really print anything besides console logs. My JavaScript has shown. And so what this does with your hypervisor is that it strips it down to the barest of bones. So you don't have these unnecessary device drivers anymore. You have something really, really, really simple. And this also comes with the effect of your guest OS, so anything within the virtual machine, now understands that it is no longer hardware. So it's not being lied to anymore, it's being told the truth, that it is a virtual layer. And so because it understands that it's virtualized, it makes optimized system calls down to the physical hardware level, or to the hypervisor and then to the physical hardware level. So you have optimized calls. You're not trying to pretend to each layer that you're hardware by having all of these drivers and hardware emulation. If you are not familiar with micro VMs, you might have heard of AWS Firecracker. Firecracker is a really popular VM that sort of spun out from AWS. And the reason this came about was because they had issues with Lambda being really slow. So Lambda has the issue of slow startup times. It also has the issue of like kind of issues with isolation sometimes, because they want to make sure that like your container will run in a multi-tenant setup and nothing will actually like expose to others. And so what they did was they figured that they needed to strip down the VM to like its bare essentials. Which resulted in their VMs running in milliseconds or something like that from seconds. I don't know the specific timing between the two, but it resulted in a huge change, almost like, I don't want to put a number because I don't want to be held to it, but it's essentially the idea is that your VMs now run faster. So Lambdas run a lot faster, the cold start times are significantly faster, yes. And so Firecracker does this by sort of re-architecting that hypervisor layer, as I mentioned. And like specifically, if you are interested, they use KVM, but like not exactly KVM. They use a modified KVM because they are trying to strip it down to like, again, the smallest of pieces. And so in Firecracker, interestingly, you only have like 4 emulated devices or something like that. You have like, I think it has a timer, a clock, like a serial console, and then an on-off button. I might be wrong, but I think it's something like that. It's very, very, very tiny. And so that's essentially what is contained within that level. And so how container applications work is it works within that micro VM. So it creates that micro VM, and then a customer basically like deploys Lambda, and it containerizes that Lambda function. And so the micro VM contains a tiny, tiny, tiny operating system, and your app runs within it. And so a lot of times this is used for single workloads or serverless stuff, at least in an Amazon setting. And so how does this relate to images, which is basically what we've been talking about? Well, the nice thing is that with micro VMs, you actually can use container images, because a lot of times they're trying to kind of take the revolutions or like the upsides to containers and like put it back into VMs. And creating a VM image is really frustrating because you have all these resource constraints and things you need to optimize for. But in a micro VM, like Firecracker, you would basically use an OCI compatible container image. So you could take a Docker image, for example, and have things run, and it would be grand. And of course, like there's some config that it might add as well, because again, with Firecracker, like there's some internals that you kind of have to understand. But if you really wanted to use like the bare essentials of just like a simple Docker file that you would containerize anyway, I think there's a tool called Ignite that allows you to essentially deploy a Docker file like very simply, and then it does like the internals of like configuring that to the micro VM. But again, like there are these tools that allow you to work with them, and the idea being that it simplifies the way you work with VMs without having to like actually create a VM yourself. And so just to like kind of put it all together, you have like VMs, containers, micro VMs, and they have specific use cases for each. There's trade-offs, as I mentioned, very clearly, I think. But the idea being that for each, there is a use case. So in VMs, it works if you're working in legacy systems or systems where you need incredible isolation or privacy. And in containers, you have the added effect of composability. So a lot of times, if you have apps that you want to spin up or services, microservices, it's great. And micro VMs are specifically for single workloads. So Lambda, serverless, those are like specific examples. But literally any workload that you need to spin off and like have it do a thing, it works perfectly for, because you don't have to spin up an entire environment. So it's worth noting, since I've talked about all these environments, I have to give a moment to unikernels. If you're unfamiliar with them, that's great. But unikernels is the tiniest of images. It's sort of like the nichest of like technologies, because the unikernel people are like very, very, very evangelical about their technology, but not a lot of people want to use unikernels, because again, it has like a very specific needs. So what a unikernel is that it is a lightweight, like single address space machine image, meaning that it packages your app and like very specific kernel dependencies. So for instance, in a traditional VM, it sort of takes everything. It's like, I'm going to take an entire computer and then build it and run it. But in a unikernel, it sort of internally pulls out like the kernel features that your app needs, and then it sort of packages it into a tiny app, and then it runs it. So it runs it in like much faster than a VM and much, much faster than a container. But it is, and like, it is a bit weird in that way, but there are tools out there, like I think Unik is one of them, which like a lot of the unikernel folks have been working on, which offers like a Docker-like interface. So you can work with a unikernel without having to like write a completely different programming language to make it work, or like understand the internals of kernel stuff. So understanding all of this, like virtualization, containerization, micro VMs, unikernels, is great. But the key to like figuring out the best strategy to deploy is understanding what we have at like what platforms we have access to. So when we deploy apps, we have like infrastructure as a service on one end, and you have platform as a service on the other end. And so when you deploy, you would have to think about the level of control that you want and what you have access to. So when you virtualize, or when you think about virtualizing in like the very traditional sense, you're generally dealing with the infrastructure as a service layer. And this is what gives you like that level of control. So you're essentially like provisioning a server, you're managing networks, you're doing all of that level of control. And so examples of these would be like if you used EC2 or if you used Azure VMs. If you wanted to go even deeper level, you could use like, I think Google Cloud has like a bare metal solution now, and then there's like NetActuate or whatever. So you'd basically be like renting server space, like an actual like box, and then you would provision your own like virtualization on top of it. So that's like really deep in the stack, where you're essentially like running your own, almost to the point of like building your own server rack, but not really. And then on the other end, you have platform as a service, which is sort of like managed infrastructure, so to speak. So if you were to containerize stuff, generally you're dealing with this layer because you're containerizing an app and then sending it off to a server. And the platform sort of handles all of those like virtualization or whatever it does on its backend for you. For micro VMs specifically, the interesting thing is that it is a virtualization layer, and so if you wanted to work with it directly, you would have to do a thing called like nested virtualization if you're not using like the super bare metal stuff, because essentially with infrastructure as a service, a lot of providers like EC2 already have a virtualization engine, so it has like that Zen hypervisor that it uses. And so if you wanted to do nested, you would have to basically essentially put a VM on top of a VM. And I don't think this is supported across every framework. So like, I'm really sorry to disappoint, but micro VMs are still accessible if you use like different tools. So like I work for fly.io, so I'm biased, but you could use fly.io. We use micro VMs under the hood. So you deploy your apps similar to how you would with any platform, and like we basically spin up a micro VM on your behalf, and you have an API layer that you use to like start and stop and like do various things. And then Koyeb, I don't know how to say that name, but like they're like sort of a newish startup that does a very similar thing, and they just raised a round, so they're like definitely a competitor, I guess. But they're also one layer in which you can work with micro VMs in this case. Okay, so I know you're all really excited about more train facts, because I thought I should end with like just explaining and coming around to the story around trains. But if you are curious what happened to those boxcars, they actually didn't make it much longer than that boom. So it boomed for a couple of years. And then after that, the railroad industry, I think in the 80s, so like 10, 20 years later, got deregulated. And in like true American fashion, it caused like this rise in capitalism, and everyone basically was like, I'm gonna own my own stuff. And so railroad industries and like railroad companies bought their own boxcars, or they outsourced to a company that was created called the trailer train cars. I like really went deep on train facts for the record, but so they lease their rail cars. So they might sometimes own their own, but oftentimes they lease that. So similar to how we lease stuff, or how like infrastructure companies lease us server space, and we like agree to that somehow. And so the railroad industry kind of has this agreement where they lease or they borrow rail cars. But the upside is that that particular time or period in history resulted in really colorful rail cars. If you are interested in trains, there's a whole thing around them. And so again, just to wrap up, when it comes to deployments and when it comes to like globally shipping your applications, you have a lot of options, and understanding the underlying systems kind of determines how you can build. And that is all. Thank you.